Welcome. In this video, I'm going to be working the problems from Algebra 2 Homework 9.1. We're going to be practicing our exponential functions. And I really want to emphasize that I need you to work these problems on a separate sheet of paper. Okay, right now I am telling you, hey, if you crammed your answers in with these, I need you to copy them on a separate sheet of paper, okay? Because I'm not going to be willing to take this from you. Okay, so what I'm going to do is I'm going to model that. I'm going to go, and I'm not working under the document camera today because I'm at home, but I'm going to go over and I'm going to emulate a sheet of notebook paper, and we are going to work on a sheet of notebook paper here. All right. I'm not expecting you to copy the problem or anything like that. I just brought these in so we could, what we're actually trying to graph here. Okay, for problem A, y equals 1.2 to the x is going to be exponential growth. Okay, so let's say, right, the general picture of exponential growth is like this, and the y-intercept, I think that's what I'm going to do. I'm just going to label the y-intercept for all these graphs. So 1.2 to the 0 power, that's equal to 1. Okay, for B, this is 0.8 to the x, 0.8 is less than 1, that represents exponential decay. So, go over here, and I'm going to draw it like that because it's 0.8 to the x, it's positive 0.8 to the x. Okay, so it's going to just be, have an intercept of y equals 1. For C, okay, y equals 3 to the negative x, that's also decay. Because I think I did this one in the examples in the book. Okay, that's the same as 1/3 to the x, so that's decay. So I'm going to say, all right, it's going to be the exact same graph I just drew. And these are just sketches. They do not need to be perfect or anything. That's why I'm working on lined paper and not graph paper, right? For D, let's see here. Okay, -3 to the x is going to be growth, but it's going to be upside down growth. So it's going to look like that. Okay? It's going to be always negative because 3 to the x happens first before multiplication by -1 because of PEMDAS. So the y-intercept is going to be the negative of 1. And then it's just going to grow negatively. Okay, and that was, I feel like I could do a little better than that. Okay, that was my attempt at it, and I don't know, maybe that's a little better, maybe it's not. That's kind of how it goes. Sometimes you take a risk, try to make something better, you make it worse. So, okay, let's keep it moving. E is 2 times 3 to the x, that's going to be growth in a positive way, but it's multiplied by 2, so okay, I'm much better at drawing exponential growth than negative exponential growth, I'd say. Okay, so wait, e is 2 times 3 to the x. Okay, so that would be a 2 here. For f, we've got -2 times 3 to the x, which will be very much like d, except it'll be, -2 times. Or no, I guess it'd be twice as far from the x-axis. It's already negative in d. Okay, so this is going to be exponential growth in the negative direction. So that's a -2 there, because -2 times 3 to the 0 would be -2 times 1, that's -2. Okay, for G, I'm seeing -2 times 3 to the negative x, that's going to be decay, but in the negative direction. So draw it like this. Say, all right, -2 times 3 to the negative x, okay, it's going to be decay towards 0 from the negative direction. Okay, and again, y-intercept of -2, because if I plug in x equals 0 here, I'll take 3 to the 0 first before multiplication by -2 because of PEMDAS. Okay, and then, yes, h. 3 to the x minus 2. This is going to be growth, but moved down by 2. So maybe I'll just give myself kind of an even x and y field. Okay. For the y-intercept, it's going to be, plug in x equals 0 there, 3 to the 0 is 1, 1 minus 2 is -1. Whoops. But it's kind of the same exponential growth in a positive direction, because I'm seeing positive 3 to the x. Okay, and what's going to change is that, related to this horizontal asymptote, Okay, I'm just going to always be greater than -2 instead of always greater than 0. And so that's us, sketching some graphs. All right, now number 2, we're going to just solve some equations, and it looks like I forgot to put f in there, and I can't really think. Let me make sure there wasn't anything in my Microsoft Word file. No, it's still blank in my original. I think I'd probably just intended to put a 6th one in there just so that there was 6 of them, but that's not going to be necessary. Okay, so we're going to start off with 2 to the 3b plus 4 equals 16 to the 2 minus b. Okay, these are not the same base, so I need to do some work to make sure they are the same base. Okay, 16, I can write that as 2 to the 4. And then I'll say, all right, 2 to the 3b plus 4 equals 2 to the 4 times 2 minus b. Okay, which means at this point, okay, I've got the same base. I can set the exponents equal to each other. Right, so I was going to say, all right, 3b plus 4 equals 4 times 2 minus b. I'll distribute. Maybe I'll add 4b to both sides. Subtract 4, divide by 7, and get b is 4 divided by 7. I'll just kind of move off to the side and work b, and then I'll just start clearing stuff off after that. All right, 2 to the b plus 1 equals 1/2 to the b. Okay, again, not the same base, but 1/2 can be written as a power of 2, so I can use the same technique. Okay, 2 to the b plus 1. Okay, 1/2 is 2 to the negative first power. And so I'm going to say that's 2 to the b plus 1 equals 2 to the negative b. Now that I've got the same base, I can set the exponents equal to each other. And I can say, all right, b plus 1 equals negative b. I'll add a b to both sides. 2b plus 1 equals 0. 2b equals negative 1. b is negative 1/2. All right, c is 2 to the b squared minus 4 equals 1. Okay, now what we're really doing here, I'll work off to the side in red. Okay, we're going to say that 2 to the b squared minus 4 is equal to 1, which I could write as 2 to the 0. But I think that we could solve this one kind of like, more with our eyes and be like, okay, well, something to the 0 is equal to 1. That's the only way we can get 1 out of an exponential situation. So I'm just going to grab b squared minus 4 and set it equal to 0. And at this point, we could factor or we could solve directly, right? If we wanted to solve directly, we'd say b squared equals 4. We'd take the square root of both sides. We'd remember our plus minus. But it's been a while since we factored on a difference of 2 squares, so I'm going to do that, right? Because b squared minus 4 is the square of b minus the square of 2. So that'll be b plus 2 and b minus 2. That's multiplying together to equal 0. We're going to see that b is equal to 2 or b is equal to negative 2. And you can test both of those and see that both of them will get you 2 to the 0 equals 1. So those are solutions to C. All right, for D, I've got 8 to the 2b minus 2 equals 32 to the 1 minus 2b. And again, although 32 is a multiple of 8, that's not really what we're going to be working on here. We're going to be working on the fact that both 8 and 32 are powers of 2. So I'm going to say 8 is 2 to the third. And 32 is 2 to the fifth. Now I'm going to, this is a situation where I would multiply the exponents. So 2 to the 6b minus 6 equals 2 to the 5 minus 10b. Right, I'm distributing the 3 over the 2b and the minus 2, and I'm distributing the 5 over the 1 and the negative 2b. And now that I've got these things with the same base, I can set their exponents equal to each other, and I can say, all right, 6b minus 6 is equal to 5 minus 10b. And I might add 10b to both sides. Then I might add 6 to both sides. And then I'd get b equaling 11 over 16. And then the last one is E. Okay, and this one looks totally different. It's like, oh, there was nothing like this on the notes. But we have worked something like this already in this class. Okay, what we're going to do is we're going to look at this as like a kind of a quadratic equation, except the variable instead of x is 2 to the b. I think we did these with like where the independent variable is x squared when we were factoring on fourth degree polynomials. So what I'm going to do is I'm going to say, all right, so I'm going to copy the problem. 2 to the b squared minus 3 times 2 to the b plus 2 is equal to 0. I'm going to say let t equal 2 to the b. And I'm pretty sure I made sure that this would work out. I feel like I'm having doubts now, but it's all right. All right. Then what I've got is a t squared negative 3t and positive 2 equal to 0. And we would be able to factor that, right? We could say that this is t minus 2 times t minus 1. Okay, yeah, this is going to work. Okay, and these things are multiplying together to equal 0. That's only going to happen when either t is equal to 2 or when t is equal to 1. And then I'm going to substitute back on t with 2 to the b. So 2 to the b equals 2, or 2 to the b is equal to 1. And that's going to be, okay, 2 to the b equals 2 gives me b equals 1. And 2 to the b equals 1 gives me b equals 0. These are the types of exponential equations that we can solve right now. In the next lesson, I'll show you how to solve 2 to the b equals 5, right? So it's not exactly a perfect power of 2. But for now, these are the ones that we can do. And that was good. I'm glad we did that example. All right, number 3 is a graphing problem, or something that's building up to a graph. We've got f of x equals 2 to the x minus 4. And we're going to find the domain, range, x-intercept, y-intercept, values of the function, some as decimal numbers, some in simplified radical form. That'll be nice. It'll be a chance to review what we learned in the last unit. Then we'll make a sketch. Oh, and then an increasing, decreasing question. I forgot to put that on there. All right, so let's start with the domain and range. So the domain of any exponential function is going to be all real numbers, because we can plug in any number we want in as an exponent, right? 2 to the x, we can plug in any x. Okay, the range, okay, 2 to the x is always positive. Think about that, because 2 is a positive number, and a positive number to any power is positive. Okay, so 2 to the x is positive, so really what I've got, f of x is negative 4 plus a positive number. That's going to be y is greater than 4. If you wanted to do the thing we did in the last unit with the radicals and say, all right, start with 2 to the x is greater than 0, and then add negative 4 to both sides, and then substitute 2 to the x minus 4, that's what y equals, that's how you would get that. Okay, if you are algebra robot and you prefer that, that's what you can definitely do. But you can also just kind of look at it and say, okay, 2 to the x is always positive, it's going to be greater than that number that's added off to the side. All right, b, for the y-intercept, we let x equal 0. That's one of the big themes in this class. So f of 0 equals 2 to the 0 minus 4. So we're going to do that 2 to the 0, exponents before subtraction, so 2 to the 0 is equal to 1 minus 4. That's going to be negative 3. Okay. I'm thinking, maybe I'll shift over here to do the x-intercept. The x-intercept is going to happen where y is equal to 0. Okay, so I set y equals 0. So 0 equals 2 to the x minus 4. And I'm going to try to solve this as best I can. Okay, we don't really know how to solve this yet, so I think we're just going to have to look at this and be like, is there any x values that I can think of that would make this equation true? Yes, if x is equal to 2, I would have 2 to the 2 is 4, minus 4 is 0. So I'm just going to say x equals 2. Again, I'll show you more about solving these equations in the upcoming lessons. Okay, so x equals 2 there. Y equals negative 3, I've got an x-intercept and a y-intercept. Now, I think we're going to just have a brief interlude of approximating function values. That's not going to really be important for my sketch, but f of negative 1 is going to equal 2 to the negative 1 minus 4. Okay, 2 to the negative 1 is 1/2. So if I have 1/2 minus 4, as for a decimal, that's negative 3.5. And then if I take f of negative 2, something pretty similar is going to happen. It's just going to be 2 to the negative 2 minus 4. 2 to the negative 2 is 1 over 2 squared. So that's a quarter. A quarter minus 4 would be negative 3 3/4. So negative 3.75. And then E, okay, I think I should be able to maybe fit this in. Let's see, I might have to zoom out a little bit. For E, find the value of f of negative 0.5. Simplified radical form. All right, so 2 to the negative 1/2, or maybe I'll write it like that. Let's see if I can jog your memory a little bit. Okay, so that's 1 over 2 to the 1/2 power minus 4. And that's going to be 1 over the square root of 2 minus 4. And 1 over the square root of 2. Okay, I hope that we rationalized that number enough in the previous unit that you just know that that's root 2 over 2. If not, you're going to multiply by square root of 2 over square root of 2, and you're going to see that this is equal to root 2 over 2 minus 4. And, like, yes, we could combine those into a single fraction using the common denominator, but I'd say that's still simplified radical form as far as I'm concerned. All right, then, and by an exact value, we mean it has the square root in it. It's not like a decimal number or anything. Okay, now for f, we're going to give a sketch, and sketch of f of x. Let's see, I think I'm going to go with the x-intercept, y-intercept. And that's 2 points. That's enough, because I know that this is going to show exponential growth, because it's positive 2 to the x minus 4. So I'm going to say, all right, the y-intercept was negative 3, and the x-intercept is 2. So I'm just going to kind of have my graph like that. Okay. I'm also going to point out, okay, so since y is greater than 4 is the range, y is greater than negative 4. Whoops. Wish I'd caught that sooner. But that means that y equals negative 4 is going to be a horizontal asymptote for the graph, and so we can sketch that in too. Ooh, and I almost moved on without addressing if f was increasing or decreasing at x equals negative 0.5. All right, so right here, x equals negative half, it's going to be, say it's right there. Okay, and it's not increasing very much at that point, but it is increasing, because this function f of x equals 2 to the x minus 4, this is increasing for all x. First of all, just like you put a bigger exponent on 2, you're going to get a bigger result back. But also look, like as I move left to right on the graph is always going up. So I would say, you know, f is increasing, whoops, at x is negative half. Okay, and that's all for this problem. All right, now number 4 is another, let's sketch the graph, except this is e to the negative x. All right, now if you did not watch the video yet on the number e, you're going to need to do that. So maybe I will even leave myself a note to add a card, and you know, if you have not watched that video yet, I bet I'm going to be putting in a link to it right about there. But if you already did, or you just, you know, heard me when I said, or heard somebody else say that e is just some number between 2 and 3, then we'll be good to go. Okay, this is an exponential function, e to the negative x, so it's going to have domain all real numbers. There's not any number that I can't put as an exponent of e. Okay, the domain is all real numbers. The range, okay, e to the negative x, e is a positive number. A positive number to any power is going to be positive. So I've got a positive number plus 2 has got to be bigger than 2. So let's say y is greater than 2. If you wanted to build this up algebraically, you could say, hey, e to the negative x is a positive object. I could add 2 to both sides. And e to the x plus 2, that's y, so y is greater than 2. That's how you would do that if you wanted. Okay, so domain, range, y-intercept. Okay, we're going to plug in x equals 0. And then g of 0 is going to equal e to the 0 plus 2. Okay, exponents before addition. Okay, so 1 plus 2, that's going to equal 3. The x-intercept, that would be where y is equal to 0. All right, and this is a little tricky of me, but I'm glad I did, because we need to be kind of running into this this line of thought before next class. Okay, so e to the negative x plus 2 is equal to 0. Okay, that means e to the negative x is equal to negative 2. And, you know, maybe you heard me earlier when I said that e to the negative x is always positive, so it can't ever be negative 2, so this is not going to have any solution. But also what I'm going to say is e, that's like 2.718 something, I think. It's a positive number. And you're not going to be able to take a positive number to a negative exponent or a positive exponent or any exponent at all that's a real exponent and get negative 2. Okay? But you could also say, okay, we're having no solution here for the same reason as, you know, we're not seeing any y equaling 0 in the range. Okay, just thought I'd point that out too. All right, a sketch of the graph of y equals g of x. That's my x-axis. I'm going to show some exponential growth, except it's going to have that leveling off is going to happen above the x-axis. It's not going to be able to approach the x-axis anymore because I've got that plus 2. So I thought I'd maybe put the y-axis in about there. And, okay, so that's y equals e to the x plus 2. Or, oh, yeah, that would be e to the positive x plus 2. Okay, mess that up. This needs to be exponential decay. And so I like that y-axis, but I'm pretty bad at drawing exponential decay on a tablet, so I think what I'm going to do is I'm going to let that be y equals 2, the thing that we're kind of approaching. And, oh, that looked pretty good. Okay, so I'm going to draw in my asymptote here. That's going to be 2. Oh, and that actually kind of fits in with the scale of my lines. Okay, so that's y equals 2. This y-intercept is y equals 3, and that's a nice sketch. Okay, is g increasing or decreasing at x equals negative 0.5? It's going to be decreasing because the function is decreasing everywhere. Okay, the bigger x is, the less e to the negative x is. And I'll let you think about why that's true. If you're not seeing why that's true, I would encourage you to come in and talk to me, you know, sometime in the morning. I could probably show you why in about 30 seconds. All right, so I'm going to say g is decreasing at x equals negative 0.5. Okay, we could say g is decreasing at all x, but they just asked us about x equals negative half, so let's just like restrict our level of responsibility here. All right, with this one, we're going to start off with, you know, a situation, and we're going to write an exponential function that models the scenario. Okay, so I think I might copy in the skeletons that we saw in the lesson. And so the first one is for a period of time, an island's population grows at 3.8% per year. So that's going to be exponential growth. All right, so for y is going to equal the starting value. The current population is 1,543 times 1 plus the growth rate is 3.8%. So that's 0.038, because 3% is 0.03, right? So 3.8 would be 038 to the t. Now, if you wanted to combine this and write that as 1.038 to the t, you'd be welcome to do that. But if you wanted to leave it at this step, you'd be good to do that too, at least in my class, I would say. All right, for B, carbon-14 decays. Okay, that's going to be exponential decay. I made sure to use one that uses that actual terminology. 12.1% per millennium. Okay, and I'm going to just point out over here, t is going to be measured in years, and for the second one, t is going to be measured in millennia. Let's spell millennia. 2 N's. No. Yeah, that looks right. All right, so current mass of the sample is 135.2. And then that would be 1 minus 12.1%. Well, 12% is 0.12, so 12.1 is 121 to the t. Right, and we could go and figure out what 1 minus 0.121 is and write that, but I don't think we really need to, because that's still going to be a valid formula. We could type this into our calculator and get just the right graph. All right, now here's the thing that I was telling you about in that kind of follow-up video with the calculator example, is the recursive formula thing, and we're going to see that for the next two. And so in Texas Algebra 2, we need to be able to be given a recursive formula and recognize a recursive formula for, really it's a geometric sequence, and recognize the exponential formula that we could write for that. All right, so hn, the nth height of a super ball bounce, is 2/3 of the bounce of the height before it. Okay, the first bounce had height 3 feet. So what we're going to do is we're going to say, all right, the first bounce is 3 feet. The rate, or yeah, not really the rate, let's say the number that I'm multiplying each time to get from one bounce height to the next is 2/3. So I'm going to say, all right, in this case, y is equal to 3, that was the height of the first bounce, times 2/3 to the, I kind of, let's just say t. Yeah, because when t is 0, oh, that's the thing. Okay, yeah, that was what I was going to get at, was, all right, the first bounce had height 3 feet. So when I plug in t equals 1, I need to get y equals 3. And that's what can be tricky about this, is that we just need to make sure that it works, right? But when I plug in t equals 1, I'm going to have height 2. That's the second bounce. So I think what I need to do here is just do t minus 1. Okay. And t is like number of bounces. And for D, y is going to equal, okay, there are currently 130 students in the program, times 11/10. Okay, we've seen that one. I think that was in the calculator example. Yeah, it was a growth rate of 10%. 130 times 11/10 to the t. Okay, but there are currently, right now, 130 students in the program. Maybe we say right now is t equals 0, and so that would be 130, and that would be okay. We could leave that as t. Okay, and so these, those little manipulations that you have to do, those are dictated by the situation, right? Number of bounces, number of students in a program over a year. That's where we're just going to have to take a step back and think about it for a second and write a formula that works. That's why these type of questions work really well in multiple choice, is because there will only be one that could work, whereas in a free response situation where you're creating your own, yeah, I might think of one formula and you might think of a different formula and they'd be equivalent, but they'd look kind of different. So that's why we go multiple choice a lot there. All right, and this last one, this one's nice. I like this. I think I found at least the figure 2 problem. I found this one in an old textbook that I hadn't looked at in a while. And that's what I found this year, is there's a lot of stuff I'd forgotten about that were in those old textbooks that I really did like. And so I'm going to try to, for the rest of the year, try to bring out some of that good stuff. So we've got, let's just do the figure 1 stuff. That has to do with A and B. Okay, what is the value of A? Okay, I told you in the lesson that the meaning of A here is it impacts the y-intercept. It's a vertical stretch. But, outside of not having anything added to it, A is just going to be the value of the y-intercept. Because right here, okay, I'm going to say, well, x equals 0, y equals A times B to the 0, and okay, B to the 0 is 1. And so y is equal to A, and y is equal to 3, so A is equal to 3. For B, give a possible value of B. We don't know what B is, but we can see that we've got exponential decay. So I might say, B equals 0.7 or something. Really, B could be pretty much anything, I'd say, between 0 and 1. Okay, it's probably pretty close to a half or something, because it's not like really extreme exponential decay, like it's not going down really hard to the x-axis, and it's not really flat either, so it's, I don't know, it's probably some medium multiplier, but we don't really have the tools to say. It's just important that B is between 0 and 1. All right, now in C, we've got F, G, and H. Well, it looks like we can determine this based on the y-intercepts, but because we can see one has a y-intercept of 1, another one has a y-intercept of something else, and the third one has a y-intercept of 3. Okay, yeah. So the one that has a y-intercept of 3 will be this one that's got 2 added to it after the fact, because c to the 0 will equal 1, and okay, so I might start with that one. So that's going to be g of x. I think I'm going to just sketch on the figure. Okay, but actually, no, you're working this on a separate sheet of paper, so I'm going to, I know what I would do. You know, what the most responsible student is going to do is actually copy these graphs here. Hate to say it, but, you know, there it is. So we've got that one that's coming from a pretty similar place, but just goes up a little higher. And then this one that's coming in from, like, pretty flat and going about like that. Okay, that's how I would draw it. All right, so I would say this, we determined that was G. And let's see, I should probably use like a color here. That's going to be G. All right, then the one at the bottom, that's going to be F because the y-intercept is 1. Okay, when I plug in x equals 0, I get c to the 0, that's going to be 1. Okay, so I'm going to call that F. Let's see, where am I going to put that? I'm going to put that over here. I'm going to give that an arrow, and I'm going to go over that one in green. Not sure how this is looking on screen. I'd say it looks okay. Okay, and that must mean that h is the one in the middle. Okay, g of x equals c to the x plus 2 is going to be the exact same as f, just move to the left by 2. Okay, I didn't draw the best sketch ever, but that's what's kind of going on with there. And figure 2 can be a little bit deceiving because they're graphed on the same like x interval. But yeah, that's how we're going to make that determination. Oh yeah, and so I needed to say, okay, h is the one that I've graphed in blue. Okay, and that's all the problems for this set, right? Yep, that's it. That's all for this video. Thanks for watching. Hope it helped.